Okay, it's time for the DHSS model. Now, and I'm going to start with a brief intro. So what is the DHSS model? It's named after these four guys: Dasgupta, Heel, Solow, and Stiglitz. And basically this name for the model has kind of, in the literature, we've sort of converged on this name over the 40 odd years since these guys' papers initially came out. So in the older literature this term doesn't exist, but these days it's pretty accepted. Dasgupta, Heel, Solow, Stiglitz model. The papers they wrote were in a special issue of the Review of Economic Studies in 1974. And what triggered this whole interest suddenly, Review of Economic Studies is a so-called top 5 journal. It's one of the top 5 most prestigious journals in economics. What triggered this interest in sustainability, which is what the model's about, it was the oil crisis of the 70s, you can Google it, and it was the report of the Club of Rome called The Limits to Growth. So the oil crisis kicked off, I guess, actually in 74. But I guess there were indications of it before that. Limits to Growth, I'm pretty sure, came out in 72. And basically the Limits to Growth report said, we're all going to die. Or it sort of said, look, this exponentially growing economy on a log scale like this, it's not sustainable, we're going to fall off a cliff. At some point, probably round about, I think they said round about 2050. We're going to run out of natural resources, and even if we don't, we're going to choke on pollution. It's basically what they said. And so then, triggered by this kind of stuff, some of the most well-known macroeconomists at the time piled in and started modelling. And this is kind of where sustainability modelling sort of starts, really. So we're going to start by looking at this model, seeing what we can learn from it and what we can't learn from it. So it's a bit like the Solow model. It's the same Solow. Solow shows us that capital accumulation can't give long-run growth. So that's what we do learn from it. What we don't learn from it is what does give long-run growth. I mean, it has to do with technological change, it must have, but how does that happen? He doesn't have the answers. This model is kind of similar. There's a lot more that we don't learn from it than what we do learn from it. Okay, that was a quick intro. I'm going to pause the video now, collect my thoughts, and we'll go straight into some of the modelling. Okay, so we're just going to pile straight into the model, actually, and I'm just going to go straight to these 3 cases. So I've gone to page 3 of the slides. Page 2, neoclassical growth and non-renewable resource supply, which is effectively DHSS. 3 simple cases. Okay, and I'm going to start with case 1. And in case 1, as you see, the sort of non-renewable resource is actually just land, or a flow, a constant flow of something from outside like sunshine. So it's never used up. Okay, so there's no big problem with using something up and crashing. So this is a very special case for the model. Okay, so what does this case look like? We have households and firms. Households supply labour to the firms, and the firms produce goods, Y. Some of that goes to consumption, C, 1 minus S times Y, and some of it goes back into the firms in the form of investment, I, which is SY. Hopefully this reminds you of something. Okay? Yeah, it's the Solo model so far. But we add to the Solo model that there's also another input needed, which we call R. And in the picture, I'm going to follow the picture, it's sunshine. But the important thing is that the flow of R is exogenously given and fixed. Okay, so it could also be just the area of land. We need land to produce, and we have an area of land R, and it's fixed. Okay. And so then we need to change Y in Solo. We had Y as ALL to the 1 minus alpha, K to the alpha, didn't we? But now we need to adapt that, and we have ALL to 1 minus alpha minus beta, K to the alpha, R to the beta. So we stick with Cobb-Douglas, but we've added an extra input. Okay, and we also assume, a bit like before in the Solo model, we assume that AL dot over AL is G, so that's a constant growth rate, isn't it? And we have the standard capital accumulation. Notice we're in continuous time, so we've got K dot is SY, so how much new capital, how much does capital grow in one period? It's how much capital we save in that period minus how much capital depreciates or blows up, disappears. Okay, so that's the rate of, well, that's it's not the rate of growth of capital, but it's the rate of accumulation of capital. Okay. So that is basically the model. So it's an incredibly simple model here. Yeah. Yeah, now I'm going to pile straight into the math, and we'll talk about interpretations and stuff later. But remember, I can't remember how much I talked about this before, but the right question to ask about models is not, are they like a good representation of reality, but are they sort of correct? The right way to think about models is, are they useful? Yeah. So the question is, does this model help us to understand what's going on in real economies, which we know are way more complex? Okay. And we're told, page 3, assume balanced growth, characterize the BGP. So, if you like, you can stop the video and try to work out how to do that. But I'm going to ask you to do that in the next version of this. Here I'm going to plow on. So we assume balanced growth. What do we know on balanced growth? We know that the state variables grow at constant rates. Okay. So K dot over K is constant, yeah? If K dot over K is constant, then that means that K is growing at a constant rate, okay? So if we're on a balanced growth, K dot over K is constant. We're told to assume balanced growth. So then we assume that K dot over K is constant. But we've got this equation. And that implies if we divide both sides by K, we have K dot over K is S Y over K minus delta. Okay. We know that this is constant, we've assumed that. that is just a parameter, so that's always going to be constant. S is also a parameter, that's just constant. So that means that y over k must be constant. Y and k are both variables, aren't they? If the ratio of the two variables is the same, they must be growing at equal rates. Okay? If we add 1% to y, we have to add 1% to k to keep y over k constant, right? So that implies, remembering growth rates, that means that y dot over y is k dot over k. Yeah. If we add 1% to y, we have to add 1% to k. This is the same. Okay. So this is like the standard approach with this model. Okay, you're going to need to use this approach in lots of different cases, and if you look at exercise problems, old exams, you need to use this approach in quite often. Okay, so this is important. So, where do we go from here? So we know that y dot over y is k dot over k. But what is y dot over y? We've got an expression for k dot over k, so we can't do so much with that. But what is y dot over y? Well, we've got an expression here for y, haven't we? So we should be able to say how y is going to grow. And this is going to be some math which some of you will be new for many of you. Okay. So yeah, let me take this step by step. So let's assume y is equal to L. Okay, let's take this super simple. And let's assume that L is a function of time. Okay. So y is also a function of time. Yeah. Then what is dy dt? dy dt, how does y change with time? Which we call y dot. That's just notation. That must be equal to dl dt, i.e. L dot, right? That's pretty straightforward so far. Okay. I'm going to gradually add stuff to this now. Now let's assume that y is equal to AL L T. Then, and here AL then I'm assuming is constant. So then we get y dot is AL L dot, right? dy dt is AL times L dot. And then if we divide through by this, we can divide, these two are the same thing, so if we divide the left hand side by y and the right hand side by this, we get y dot over y is L dot over L. So even though y and L aren't the same, their growth rates must be the same, right? Because this is just a constant. Okay. Now imagine that AL is also a function of time. Okay. So now imagine that both AL and L are functions of time. I'm going to save ink and not write the t's, but they're both functions of time. What then is dy dt, or y dot? Well, what is going to make y grow? This is the product rule, yeah? It's if this grows, growth in this times this plus this times growth in this, yeah? So what is going to make y grow over time? If this is going to grow over time, that will make y grow. And if this grows over time, that will also make y grow. And those two effects are kind of independent. We have to add them together. So it's AL dot L plus AL L dot. Okay. But now, again, let's divide the left-hand side by y and the right-hand side by ALL, which is we can do because y and ALL are equal. So then we end up with y dot over y. Divide this by ALL, what do we get? We get A dot L over AL plus divide this by ALL and we get L dot over L. So the growth rate of y is the sum of the growth rates of AL and L. Okay? So if AL is growing by 1% a year and L is growing by 2% a year, y will be growing by 3% a year. Okay. That is slightly not exactly correct interpretation, but a kind of intuitive way of seeing this. Yeah. Okay. So now I'm going to go all the way and look at this. Because now we have y is ALL, so 1 minus alpha minus beta, k to the alpha, r to the beta. So what's y dot? And now we have the third thing to think about, which is this alpha. So we're using the same rule. So dy dt, I'm going to write it as go back to writing dy dt. Okay, change my mind. dy dt. So y is a function of AL, L, K, and R, and all those are functions of t, right? So how does y change with time? It's how y changes with AL times how AL changes with time, plus okay, the sum of all those four terms is how much y changes with time, the rate at which y changes with time. dy dAl times dAl dt plus dy dAl dL dt, dy dk dk dt. Okay. That is, I think, what we call the... I always mix these up, these names, but this is product rule, isn't it? Or is it chain rule? It must be product rule. Okay, so what is this? dy dAl. What's that? So now, another new thing for this one compared to what I did before, we're going to differentiate like economists. I think I talked about this before. So what does that mean? We've got, effectively, if we bring this inside, we've got AL to the 1 minus alpha minus beta, haven't we? So dy dAl is 1 minus alpha minus beta times all this divided by AL. That's the minus 1, yeah, on the power term. Divided by, instead of that minus 1, we say everything divided by AL, and everything is just y. So it's 1 minus alpha minus beta y over AL. And dy dL is 1 minus alpha minus beta y over L. Oh, and I forgot the A dot. Yeah. Plus that times L dot plus dy dk is alpha y over k times k dot. And now, because I've seen this pattern, I can write it like this, can't I? Alpha y k dot over k, instead of alpha y over k times k dot. And dy dr by symmetry is beta y r dot over r. So y dot is all this. And look at all these y's here. Y, 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 y. So I'm going to save ink here and divide through by y, but I'm not going to rewrite all this. So we have y dot over y equals, and this y a dot over al dot over al turns into just al dot over al, doesn't it? 1 minus alpha minus beta al dot over al plus 1 minus alpha minus beta. This turns into L dot over L this turns into alpha k dot over k, and that turns into beta r dot over r. Whew. Okay, so that is our expression for y dot over y. But then we've shown earlier that on a balanced growth path, this holds, right? And al dot over al is just g. Okay? And r dot over r is the constant exogenous flow from the sun, so that is 0. So again, I'm going to save ink and just change this expression. So we can wipe the r dot over r term. Instead of k dot over k, we can put y dot over y when we're on a balanced growth path. Instead of al dot over al, we can write g, and we're not told anything about population growth, so of course in a proper scientific paper you would have to say, oh, population growth is 0, but in the context of our problems, questions, exams and so on, if you're not told anything, assume the simplest. So we'll assume that population is constant too. So we end up with this. Y dot over y is 1 minus alpha minus beta g plus alpha y dot over y. So then we can take this over and say y dot over y times 1 minus alpha equals 1 minus alpha minus beta times g. Why am I writing it in this weird way? It's because I'm going to now divide through by 1 minus alpha. I can get rid of these brackets. And get rid of that. So y grows a bit more slowly than g. Or y grows a bit more slowly than productivity grows, al, because g is al dot over al, yeah? Why is that? In Solo, remember, they grew at equal rates. But in Solo, effectively we can get Solo back by setting beta equal to 0. If we put beta equal to 0, we don't need this constant input. We get back y dot over y equals g. So the fact that this input can't increase puts a brake on growth. Okay. Right. Long video, my computer's died. Assume balanced growth. Characterize the BGP. Page 3. The representative final good producer must hire labour, capital and land. What happens to the price of land over time? And I think I put this as a study question, so I'm not going to tell you, but I'm going to tell you how to solve for that, and then I'm going to end this video. So, we've got competitive producers in this sector. How do we model their choices here? We need to model their demand for land to know what the price of land is going to be, because these loads of competitive producers are competing to get hold of this constant amount of land or the constant flow of sunshine. Yeah, it's all competitive markets. So what's the profit maximization problem of the representative producer? It is PY, Y, where Y is given by this, but I'm going to take a shortcut and just write Y. That is revenue, isn't it? Minus costs, which is WLL, I think I'm getting my notation right here, minus W, oh, let's do K next, WK, K minus WR. So to work out WL, WK and WR, what do you need to do? I'm going to leave you to think about that, and on that note I'm going to stop the video.